Hi, everyone. I hope you're doing well. I wanted to go ahead and kind of apologize in advance for the sections on Achieve. As you probably noticed, section 2.6, 2.7, and now 2.8, it's really lacking in how it has you manipulate the sections. In 2.6, I can't truly see if you're understanding the use of the squeeze theorem logic. I can only see that you put the final answer of 0. In the last section where we had infinite limits, I can't see that you can show me algebraically how the infinite limits answers resolve. I only know if you get the final answer right, and I have to hope that you're doing the corresponding work correctly. Similarly, in this section is entitled the Intermediate Value Theorem. So the topic of the intermediate value theorem is trying to get you to understand that if you have a continuous curve that has a certain value at x equals a and another value at x equals b, then it has to take on all y values for any value of x in between a and b. So if I know f of 1 is -5 and I know f of 2 is +8, then I know that f of x has a solution. F of x must equal 0 for some x value in between 1 and 2 by the intermediate value theorem. So we could easily show that by hand. And hopefully you'll look through my lecture notes and make sure you understand the concepts, because you cannot understand the concepts and get these problems on Achieve correct, unfortunately. So now, without further ado, let me go ahead and show you what I did in this section. I actually like the first problem here. I'll share my screen here with you. This one's a cool problem. It's asking us to select all the graphs in which the intermediate value theorem would apply for the interval 2 to 5. Well, now, in order for the intermediate value theorem to apply, the interval that it's on must be continuous and defined for all values. Okay, so if I'm looking at that, it's saying on the interval 2 to 5. Well, this first one from 2 to 5, it is not continuous, so I can't use the intermediate value theorem on that problem. You see, I have the second one selected. Why? Well, even though it has a discontinuity, it looks like at x equals 1/2, that's irrelevant to the region that I would be using the intermediate value theorem on. On the region from 2 to 5, that's a nice continuous curve. So I can say if f of 2 is 3 and if f of 5 is 2, then there exists an x value in between 2 and 5 for any y value in between 2 and 3. So yeah, intermediate value theorem would work no problem on that, again, because it's continuous. You'll see I also have the third one here selected because from 2 to 5, that is a nice continuous function, no problem. The next one here, from 2 to 5, it has a whole discontinuity. Well, we could call it a removable discontinuity at x equals 4. So from 2 to 5, we could not use the intermediate value theorem. There does not exist a y value for all x values in between 2 and 5. So the only two that satisfy the intermediate value theorem's prerequisites are, on mine, the second graph and the third graph. Okay, next question here. Now, these are the ones where you're really not going to be able to show me that you understand the logic. So what I'm going to go ahead and do is show you what I did in order to explain the intermediate value theorem in the problems. So the first one I answered as I did because the intermediate value theorem only applies to continuous regions of functions. So I had to look at the functions that I had and only say that the ones that were continuous on the interval 2 to 5. For this second problem, I have a function given, f of x is equal to x cubed plus x. And it's asking me if the intermediate value theorem would apply, or sorry, if that the intermediate value theorem would determine that f of x takes on a value of 8 for some x value in between 2 and 3. So when I try that, I can say, well, all right, if I'm trying to look at this from 2 to 3, the intermediate value theorem would say that the y values have to take on any y value in between f of 2 and f of 3 for some x value between 2 and 3. Okay, well, f of 2, if I plug 2 into this equation, I get a 10. If I plug a 3 into that equation, I get a 30. So the only thing that the intermediate value theorem would guarantee you is that there exists some x between 2 and 3 for any y value in between 10 and 30. Now, it doesn't stipulate that every single y value between x is 2 and 3 must be a y value between 10. That's not the case. So it could go below 10, it could go above 30. It's just saying that there will exist an x value for any y value in between 10 and 30. Okay, so I would just say the intermediate value theorem would only show that f of x takes on values between 10 and 30. It doesn't guarantee any other y values. So I put no initially, and you'll see it took me 2 attempts to work this problem because initially I chose no. But they would rather you say the intermediate value theorem does not apply because the logic that I explained just a minute ago, Achieve wants you to say the intermediate value theorem does not apply since it does not show that f of x could not equal 8. That's not what the intermediate value theorem is saying. It could go above 30, it could go below 10. All the intermediate value theorem would say is that for any x value, or sorry, for any y value in between 10 and 30, hey, there's a corresponding x value between 2 and 3. It has to happen because of the continuity of the function. Okay, so we're saying the intermediate value theorem wouldn't preclude that the function could equal 8, but it certainly doesn't show it. So we'll just say the intermediate value theorem does not apply because it doesn't help show what's going on in this problem. I think no is every bit as of a correct answer as it does not apply. Does not apply almost makes you think that the function would be undefined in this region, and that's not the case. But we'll go with the answer that they want you to have. For our next one here, it's saying use the intermediate value theorem, if applicable, to determine if f of x takes on a value of 0.003 for some x in between 0 and 1. Okay, so what I'm trying to show that if this function takes on a value of 0.003 in between x is 0 and 1, what I'm hoping is that f of 0 is a number below 0.003 and f of 1 is a number above it. I tried that. Well, f of 0 is 0. That's 1/2 of what we needed. F of 1, if you plug a 1 into that equation, you'll get 3 times 1 over 1 plus 1. That denominator is not 4. I apologize for that. So if we plug a 1 in, it'd be 3 over 2, which I'll go ahead, well, I won't correct now, but I'll correct that before I post the PDF of this. But either way, whether we call that 3 over 4 or 3 over 2, yeah, the intermediate value theorem applies because one of the x values has a y value lower than what we need. One of the x values has a y value higher than what we need. So by the intermediate value theorem, there exists some x in between 0 and 1 such that f of x is equal to 0.003 due to the continuity of the curve. So we say, does the intermediate value theorem apply? You bet it does. Number 4 here. When we're looking at that, we can say, well, all right, we've got a trigonometric function in here. G of t is equal to t squared tangent t. So I'm trying to show that this function is equal to 1/2 for some value of x that they're calling c between 0 and pi over 4. Again, in order to show that, one of the endpoints has to be a value lower than 1/2. One of the endpoints has to give you a functional value higher than 1/2. That's what I tried. G of 0, 0 times the tangent of 0 is just 0. G of pi over 4, well, I get pi over 4 squared times the tangent of pi over 4. The tangent of pi over 4, pi over 4 has a sine and cosine both the root of 2 over 2, thus the tangent of pi over 4 is 1. So we just get pi over 4 squared times 1. I went ahead and got a decimal for the pi over 4 squared, and it gave me 0.617. Now, what do I know? Well, I'm trying to show that this takes on a y value of 1/2. Have I conclusively shown that by the intermediate value theorem? You bet we have. Since g of 0 is 0 and g of pi over 4 is 0.617, we know that there exists an x in between 0 and pi over 4 such that f of x, or in this case g of x, is equal to 1/2. So does g of x equal to 1/2 for some x in between 0 and pi over 4? You bet it does. So again, the intermediate value theorem would apply. Oops, there we go. For the next question here, it's asking us to use the intermediate value theorem to show if f of x takes on a value of 0.35 for some x in between 0 and 1 on the rational function x squared over x to the 7th plus 1. Okay, so I continued with my intermediate value theorem logic by just saying, okay, all I need to do is evaluate this function at the left-hand end of the interval. F of 0 is 0. Evaluate it at the right-hand of the interval. F of 1 would be 1 over 1 plus 1, 1/2. So I can say, well, I know that the value that it needs to take on, 0.35, is certainly in between 0 and 1/2. So I know that f of x is going to equal 0.35 for some x that's between 0 and 1. Yeah, this is conclusively shown by the intermediate value theorem. So yet again, we choose yes. I hate that you just choose yes, no, or does not apply on achieve. I wish they had some way of making you show this logic out. But sadly, they don't. This next problem's kind of cool. When we look at this, it's having us, oh, and I said no work for this one. So when we think about this one, we just think about the steps in the intermediate value theorem. So using the intermediate value theorem to decide which statements are always true. Says the equation P of C is equal to 4 is satisfied by some C in between 0 and 10, provided P is continuous. That is a requirement of the intermediate value theorem, so P is continuous. And you know that P evaluated at the bottom value, P of 0 is 0, and P of 10 is 20. Well, yeah, this is surely true. So since 4 is some number between y equals 0 and y equals 20, we know that there exists an x in between 0 and 10 such that f of x is equal to 4. Guaranteed result of the intermediate value theorem. Gorgeous. Check that one. The next one, the graph of a polynomial of odd degree intersects the x-axis. Well, yeah, that has to be the case. And you think, why? Why, John? Well, notice you could plug in, like if it was a positive odd degree function, you could plug in a very, very negative number, you're going to get a very, very negative y value. Plug in a very positive number, you're going to get a positive y value. So you say, well, how can you go from an x value with a negative y value to an x value with a positive y value without crossing somewhere in between a y value of 0 at that x-intercept? You say, well, you can't. By the intermediate value theorem, if one f of x has a negative y value and another f of x has a positive y value, there must exist some x in between them that has a y value of 0 by the intermediate value theorem. So absolutely, it must cross the x-axis. Just saying it has to have a y value of 0. The third one here, a continuous function that changes sign 2 times on an interval 0 to 1 has 2 positive x-intercepts. Well, yeah, obviously. If it's going to change signs 2 times, it's going to go from positive to negative back to positive. So it's changed sign twice. The only way to have that is that it's had 2 x-intercepts in between 0 and 1, which would be positive x-intercepts. That one's an easy one. The next one here, the graph of a polynomial degree 3 intersects the x-axis exactly 3 times. Absolutely not. From what we already know about cubic functions, they could cross 3 times. They could cross 2 times. It could cross once, come back down, touch at an x-intercept, and go back up. Or it could just cross 1 time, like y equals x cubed. It only crosses at x equals 0. It doesn't cross any other times. So that one is just not true at all. The only thing that the intermediate value theorem would assure us is that it has to cross once. It certainly doesn't say that it has to cross 3 times. The last one here, the graph of a function with functional values f of -3 is 2, f of 0 is 0, and f of 5 is 1, intersects the x-axis at least twice. Okay, think about this. At -3, the y value is 2. At 0, you're going down to an x-intercept of x equals 0, y equals 0. But then at 5, you're going back up to a positive y value. So how would that have to intersect the x-axis at least twice? From the information given, it only intercepts the x-axis once. It would have to change the y value sign 2 times in order to intersect twice. So like, for example, if it said f of -3 is 2, f of 0 is -2, and f of 5 is +1, then it would have to cross down and then cross back up. This only has the one x-intercept, so certainly doesn't have to cross twice. For our next question here, number 7, we go back to one where I can show a little bit of logic. Sadly, you don't have to show the logic to get the question correctly on Achieve again, but let's talk about this one. Whenever we're looking at this problem here, we can say we have the cosine of x is equal to x to the 6, and we're trying to use the intermediate value theorem to show that this has a solution. What I always prefer to do is, instead of using the intermediate value theorem to show when the left side of the equation is equal to the right side of the equation, I would rather subtract the right from the left and show that f of x must equal 0. So if I let f of x equal the left-hand side minus the right-hand side, solutions to the original would be solutions to when f of x is equal to 0. Okay, so now, as soon as I have f of x defined, I know I could plug a 0 into it. The cosine of 0 is 1, and then minus 0 to the 6th is just minus 0. So I get a positive y value when x is 0. Now, I'm looking for some x value that's going to give me a negative. Okay, no problem. I went to pi over 3. Now, to begin with, I actually went to pi over 4, but that wasn't a large enough angle. At pi over 4, my cosine was the square root of 2 over 2, but I was subtracting pi over 4 to the 6th, which still kept it positive. So I didn't want that answer. I went on to pi over 3. At pi over 3, the cosine at pi over 3 moves over to just 1/2, but then you're subtracting pi over 3 to the 6th. So I can say, well, I have 0.5 minus a much larger number here. That's going to give me a negative 0.819. Is that good? You bet it is, because I can't go from a positive y value to a negative y value without crossing a y value of 0 for some x value in between here. That's what the intermediate value theorem says. So I can say, so given what I just done, I can say that this equation has a solution for some x that we would call C in their intermediate value theorem, belonging to the set of numbers between 0 and pi over 3. I actually know it's between pi over 4 and pi over 3 if I wanted to be more precise, but this is fine. We just had to show that it had a solution, which it certainly does. We would choose yes, it has a solution, and get that problem right. For number 8, it's trying to use the intermediate value theorem to show if an exponential 2 to the x equals a linear function 3.2x. Okay, so here's what I do. Again, I think it's so much easier to use the intermediate value theorem if you'll go ahead and say, let's set up a function where we have the left-hand side minus the right-hand side, and whenever this function can be shown to be 0, then the original equation would be true. All right, just like last time, I'm going to plug a 0 into this. We know any exponential function to the 0 power is 1, and then we'd have minus 3.2 times 0 is 0, so 1 minus 0, I get a 1. Now, at this x value, I get a positive y value. I'm trying to find an x value now that would give me a negative. So I can say, ooh, what about at 1? Because this is just going to be 2 to the first, which is 2. You're going to be subtracting 3.2 times 1. That's going to give you a negative 1.2. And I can say, well, that is wonderful, because now I know, since the y value changed sign from positive to negative here, then that means that there is an x value in between 0 and 1 such that this original equation had to be true. That's what the intermediate value theorem states. So I would say, well, since f of 0 is 1 and f of 1 is a negative 1.2, we know there exists an x equals c belonging to the set of numbers in between 0 and 1, where f of x is equal to 0. That's the goal of this problem. F of x is equal to 0 means the original problem is true. We were able to solve that. So yet again, you just say this equation has a solution. Hopefully you are looking through the problems in this section instead of just blindly getting credit for it. I do plan on putting a problem like this on your first test, asking you to use the logic of the intermediate value theorem to prove the existence of a solution. So let's go ahead and look at that in this next problem. If I'm trying to prove that 4 to the x plus 5 to the x must equal 7 to the x, I can say, okay, how do I do that? First, I'm going to go ahead and let f of x equal the left-hand side minus the right-hand side. I know that if I can show f of x is equal to 0, that's going to be whenever the original equation is true. Yet again, I'm going to plug in a value of x equals 0 because I think something important happens around there. Well, when I do, I can see that all exponential functions to the 0 power is 1, so we just get 1 plus 1 minus 1 for a 1. Now, I need to choose another x value that gives me a negative. Unlike last time, I can't just go to 1. In fact, I thought about it in my head, but if I just go to 1, I'm going to get 4 plus 5 minus 7. That's going to be a value of 2. Does that help? No. I need one positive y value, one negative y value to ensure that there's a y value of 0 somewhere in between the x values. So I can say, oh, okay, 1 doesn't help, but 2 will, because as soon as I plug in 2, I'll get 4 squared plus 5 squared minus 7 squared. That's going to be 16 plus 25 is 41, minus 7 squared, 49. That's a negative 8. Now, technically, I really know that the answer is somewhere between 1 and 2, because f of 1 would have also given me a positive y value. But it's not wrong to say your solution's between 0 and 2. It is. So we can say, since f of 0 is a positive value and f of 2 is a negative value, we know that there exists an x value that we call c, so x equals c belonging to the set of numbers between 0 and 2, where f of x is equal to 0. Since that's the case, the original equation has to be true for some x value in between 0 and 2. In fact, I know it's between 1 and 2. So yeah, this has a solution, and the intermediate value theorem certainly applies. When I go to number 10, it's asking us to use the intermediate value theorem, if applicable, to determine if the equation, the cosine of x is equal to 9 inverse cosine of x, has a solution. Okay, so again, you see I've chosen, hey, the intermediate value theorem applies. Why does it apply? Well, notice what I've done here. I said, all right, here's my original equation. Let's let f of x equal the left-hand side minus the right-hand side. Now, in order to show that the intermediate value theorem applies, I need to find one x that's going to give me a positive y value, one x that's going to give me a negative y value. Then that guarantees the existence of an x that's going to give me some value of y equals 0. Okay, now, again, I just plugged in a 0 to begin with. I get the cosine of 0 minus 9 times the cosine of 0. Cosine of 0 is 1. But now, whenever I say minus 9 times the cosine, inverse cosine of 0, you've got to be thinking inverse cosine of 0. That's asking you, when is the cosine going to equal a 0? And that's at an angle of pi over 2 straight up on your unit circle. At pi over 2, the cosine is 0. Anytime you see an inverse trig function, you have to remember the answer is an angle. In this case, the answer is the angle at which the cosine would be 0. Well, the cosine of pi over 2 is 0, thus the inverse cosine of 0 is pi over 2. So I have 1 minus 9 times pi over 2. That gives me a pretty dramatically negative number. I approximated it to negative 13.1. So now I need to find a value at which the cosine is going to be a positive. So I just said, well, what about at 1 radian? The cosine of 1 radian is not going to be a pretty number. I went to my calculator to assist with that, and you'll see I just went in here and said it's the cosine of 1 radian. I got the 0.540. That's where that came from. Now, minus 9 times the inverse cosine of 1. Now, that's not hard at all. Inverse cosine of 1, that's asking you at what angle is the cosine function equal to 1? That's at an angle of 0. So the inverse cosine of 1 is 0. I get cosine of 1, 0.54 minus 9 times 0. I get the positive value I needed. So I'm thinking, fantastic. Since I have a negative y value here and a positive y value here, I know there exists a y value of 0 for some x value in between x equals 0 and x equals 1. That's what I've said right here. Since f of 0 is negative and f of 1 is positive, we know there exists an x equals c between the values of 0 and 1, where f of x is equal to 0, which means your original equation does have a glorious solution. And again, Achieve takes the fun out of it by just having you select it applies. The last one here, again, the intermediate value theorem will imply that there's a solution, but let's see why. So we have the inverse tangent of x is equal to 8 inverse cosine of x. So I can say, well, all right, f of x is going to equal the left-hand side minus the right-hand side. I went ahead and evaluated at -1. The reason is because I know that the inverse tangent of -1, that's going to be where it splits quadrant 4, and I have to use the angle of negative pi over 4. Please don't think it could be 7 pi over 4. We have to restrict the tangent function from negative pi over 2 to pi over 2 in order for the inverse tangent to exist. So it's negative pi over 4 for that part. And then minus 8 times the inverse cosine of -1. That's asking you, when is your cosine function -1? That's at an angle of pi. So you could say, I'm going to have negative pi over 4 minus 8 times pi, and that's going to give me a very, very negative value of like negative 25.9 approximately. Now, I also plugged in, what about f of 1? That was a nice thing to plug in because, again, the inverse tangent's easy to evaluate at 1. You just say, well, the inverse tangent's 1 at pi over 4 because at that point, both your sine and cosine are the square root of 2 over 2, so the tangent is 1. The tangent of pi over 4 is 1, thus the inverse tangent of 1 is pi over 4. And then we get minus 8 times the inverse cosine of 1. We talked about that in the last problem. Inverse cosine of 1 is asking you at what angle is the cosine function 1? That's at an angle of 0. And so now we can get, well, that's pi over 4 minus 0, which is just going to be pi over 4. That rounds to a decimal answer of positive 0.8. I really don't care that it's 0.8. I just care that it's positive. I have one negative y value, one positive y value, so I know that there exists an x value in between -1 and 1 such that f of x is going to equal 0. Thus, the intermediate value theorem applies. That's what I said right here. Since f of -1 is negative and f of positive 1 is positive, we know that there exists an x in between -1 and 1 where f of x is equal to 0. Glorious problem there. All right, guys, hope you have fun with this section and that you don't just blindly choose answers in there. Please do remember, I said I would put problems like this on the test where I'm not just looking at, hey, you're saying, yes, the intermediate value theorem applies. I want to see the logic of the intermediate value theorem like I've done here and like was done in our notes for this section. All right, guys, have a great day, and we'll see you back for chapter 3 in the next video. Fun stuff.